You are Ali, right?
Yeah.
Yes. I just try to remember the name. Design. Okay. You ready?
Yeah.
Okay. I try to distinguish you. Okay, that's almost 1 minute. Okay, first all right, just try to remind you, we end of last class, we after discuss the field of the classical mechanics, we think now we are going to start a new theory which go beyond the domain of classical or old domain, right? So to establish this new theory called quantum mechanics, we need a postulate because there's no direct observation. So the postulate as a basis, right, to try to establish the quantum mechanics, we base this, they are good to formalize the quantum mechanical theory. Now, in order to discuss those postulates, we need equipment ourselves, some of the required mathematical tools. So in chapter 2, I will go a little bit fast because I think you have a strong background about the math. So just try to remind you, or we are going to review what is the basic or key tools we are going to use in when we establish the quantum mechanics theory. So first, the Hilbert space. Why we introduce Hilbert space? Because we know in the chapter 1 we already said that the quantum system has a duality, right? We behavior part behavior and try to describe such duality, we introduce state function, right? So state function to categorize this both, and we introduce this wave function, a kind of a probability wave. So we are going to first discuss the property of a wave function. The wave function belongs or within the Hilbert space. So the Hilbert space sum of feature of this required for the wave function that we also require in the quantum mechanics, right? So that is we are going to try to wave function relate to this topic. That is this correct state of quantum system. So for the, what is Hilbert space? Right? Hilbert space definition. That consists two sets, right? So that is a Hilbert space. We usually use H, which is consists of two sides of the element. So which the first set is vector, right? So the first set is a set of vectors. Then vectors in Hilbert space, in more general, we are going to use psi, phi, chi, those, not R. R is just one of the position vector, right? We just take the more general case and pass this sheet. Yeah. That is a side of vector, another side, a side of scalar. Scalars, like A, B, C. But those scalars not only real, they become, most cases, complex numbers. So that is those two sides of this element build up or construct this Hilbert space. Sorry. Then there are several rules. So this is definition, right? And those side of vectors and the side of the scalars, they obey. So they obey several rules. First one is additive. Additive rule, that is for vectors. Because in particular vectors is how we addition the different vectors, right? To follow the active rules. Active rules, there are four, which is in the linear space. That is our first section of this first subsection. So I do not go to details. I just give you summarize. For example, we have two vectors, psi plus 5 equal to, you can change the position, right? A plus b equal to b plus a. So that is commutative. We take commutative. Okay, commutative. Second one, if we have three vectors, psi plus 5 and then plus chi, we can first add these two first and then add the third one, or add this the second and third together, then add this the first one. So this means associate. Third one, there is a zero vector means if there's an exist. So this vector plus any vector equal to any vector plus this one. So that means exists zero vector. And then the last one exists inverse, right? So if we have this vector plus its negative equal to its negative plus itself always equal to 0. So that means exists inverse for each vector, inverse vector. That is the additive behavior for vectors. And this is the first one, right? So second one, I'm going to write up here. Second one is multiplication rule. Multiplication. This rule is between scalar, the relation between scalars and vectors. Those are the relation between vectors follow the additive. Then for because we have two sets, right? One is scalar set of scalars, another set of vectors. So how about those? Those can be products or multiply each other and follow this. So now I'm going to if the scalar A multiply the vector, it gives another vector. That means another vector. So this product will not change the vector, but just change the vector from this one. Another vector. Then must be have so that we are not worried about the scalar. Any scalar multiply vector just increase the times of this vector by A, right? A may be larger than 1, smaller than 1, or 0, or complex numbers. So that is general case. Second one, if we have a two scalar, A plus B, and then multiply, then we can distribute, right? So that is can be A multiplied psi and plus B multiplied psi. So that is distributive. We have this. Third one, if we have a product of the scalar, we can, that is the first one, the scalar multiply the vector and then multiply another scalar. This can equal, we first multiply scalar first, and then multiply this vector. So that is associate, right? Then we always exist, we call the unity vector I. So any, sorry, this is scalar, right? If we have a scalar multiply this psi, it's always itself. Whatever in the left-hand side, right-hand side, always equal to self. So that means it exists a unity. And unity means it will not change the magnitude of the scale vector, and will not change the direction vector. And the last one, if we have this 0, if there exists another scalar which multiplied vector equal to 0, so this means it exists as 0, right? 0 scalar. Okay, this is a 0 vector, right? The addition rule gave us, if add any vector add some another one, you give 0, that means there exists a 0 vector. Here, if any scalar multiplied the vector equal to 0 means this scalar is 0 scalar, right? So that is define this, follow this, obey these two rules, additive rules and this, the multiplication rule. Now, here, that is between vectors, addition, that is a multiply between vector and the scalar. How about the multiply between scalar vectors? Right, that the vector multiply vector, we know there are only two ways, either point or dot product or inner product, another cross product, right? There's no another. So, but so far we just discussed the inner product. Then later, if we deal with this cross product, we will, in classical mechanics, we will, but the quantum mechanics usually is in most cases scalar plus. So now that is obey. And then 3, we are going to discuss the properties of scalar products. When we say scalar products is, let me give a definition. That is between vectors, right? So that is between vectors, the products. Okay, so this one, the first one, if we have, if we use this notation, right? So there's, let me see, one vector, another vector, psi and phi. We use the dot here. We use parentheses means these are scalar product of two vectors, right? So this always equal to this complex conjugate. Okay. So there's the complex conjugate. Be careful of the position. Okay, this left is psi and right is phi, right? Then that equal to change the order. So now psi is left and psi is right, but takes a complex conjugate. They are equal. If you do not change, they are not equal, right? Okay, so that is the first, the scalar product property, one of properties. Second one, if we have this vector psi multiplied a plus phi 1, b plus b multiplied by 2. So here, this is a multiplication here, right? Like this. And then addition. So this new vector psi 1, psi 1 prime, psi 2 prime is like, like here, right? And then addition of this became a new one with the inner product of this. So that's can equal to, you just dispute it, right? So that is A. I want to emphasize, this A is in the right hand side, right? So then they take out, still keep this itself. A and psi 5 psi 1 plus B 5 psi 2. Okay, so that means here is linear. Okay, this relation is linear with, I'm going to use this psi is the A1 psi 1 plus B, sorry, A plus 1 and B psi 2. So that means here, this is a psi, which is a combination of the two, and with the inner product phi. And we can just distribute it by this linear relation. So that means this one is linear with this. Then another case just for this left-hand side. If it is on the left-hand side, so we have A phi 1 plus B phi 2, and inner product with psi. That, be careful, here now in the left-hand side. So I take the A outside, we take the composite conjugate. If it's left-hand side, and later we are going to use Dirac notation, so be also, so be careful here, if this right-hand side, this scalar keep itself, right? But if the left-hand side you have to take outside, then so in this way we are going to see this is the anti-linear with which one? With we have this phi which define A phi 1 plus B phi 2. So that when we give the interpretation over, say that is anti-linear with this relation. Okay. Now then this is 1, 2, 3. So 4 is, let's look at the norm. If we have this vector inner product or scalar product itself, so that gives a magnitude of this or known, right? So that is a square, and it should be always larger or equal to 0. That means always positive and real. Not, even though the function itself may be complex, but its norm always gives us the real and positive. And those important, particularly quantum mechanics, give us a probability. This should be always real, right? Okay, so these are the Hilbert space we introduced, and then the Hilbert space we really want to. There are some others that I will not discuss. That's in textbook, but I focus those which we are going to use in quantum mechanics. So those properties. Now the first one, second one, we are going to introduce what is the basis set of the vector space and dimension, right? So that's the dimension. Okay. And basis of our vector. So Hilbert space definitely is a vector space, right? It includes vectors. Then we are going to define what is the dimension of this space and how to define the basis. So first we remind you what is linear independent. Okay. Linearly independent. If we have a set of vectors in the space, so say we have n from 1 to n, then the coefficient ai psi I equal to 0. Okay, equal to only when ai equal to 0, right? Otherwise, so if we have this linear combination and we have this, if ask 0, they only when this the coefficient 0 they can satisfy. Otherwise, we will not set at 0. So if it's set at 0, then that means they are independent, right? If only the coefficient is 0, then they satisfy this. So that is independent. Okay, then with this, so that's what is the basis? Okay, the basis set. The maximum, a set of maximum number of linearly independent vectors. So if we have a vectors, suppose this is, and they satisfy this, then okay, we say that set can form the basis in the space, but must be maximum. If we like a 3-dimension, if we have a 2 vector, they're linear independent, but it's only form the 2-dimension. So we still have means when we need to select the maximum number of the linear independent vectors. Those form the space we call it the basis set. And then when we have a basis set, we can determine the dimension. Dimension equal to, so n, dimension n equal to the maximum number of number. That is number. Linear independent. So the vector form the basis, and how many? That's the dimension, right? So that I think you all know this. Okay, with this now we say that the Hilbert space, the one side is vectors. So vectors in general we use this notation, but now since we in quantum mechanics we always introduce wave function, so we are going to introduce so-called function space, which actually is also Hilbert space, but the vector are represented by function. So now let's see. Function space. Okay, function space is now just in function space, the vectors function, right? Represented by functions. The functions like, example, if in one dimension, f, x, g, x, whatever, right? So it's just example. So you see there's a function x. Not each function for given x, we have one value that represents vector in particular value for this, right? So the scalar, okay, so then change the vector, and then the scalar product of this in the function space, scalar product, which here, scalar product, this one. This I just use the parentheses, but now in function space, those represented by the integral. So here, I think this basis means any function, right? If this is a basis, any function can be expanded in terms of linear combination of the basis, right? So that is the basis we are going to use. Now let's back to here. So that is this scalar product in the function space that is represented by integral. That is integral with respect to, for example, right? Just one dimension. Let's see an example here. That is that is psi conjugate. Okay, in the left hand side we conjugate x and phi x dx. So that is the integral. Represented by integrals. That is the function space. How to calculate this scalar product. That is this. Okay, now we have condition. This integral, okay, this integral may be finite, may be infinite. So if the function is within the function space, we require this integral to be finite. So that is a condition for scalar product. This integral, I'll just use one example, since dimension in one dimension, 3 dimension, and n dimension must be finite. If not, this function is not exist in the function space. So if it exists in the function space, the function space is one of the Hilbert space, follow all this. All the properties follow. The only difference now, the vector are represented by function. So when we do this inner product, that became an integral, right? So that is, and once we have this, so we usually to check this condition, we always say, or we call the square integrable. Square integrable. If the function or the vector in the function space is square integrable, then that's inside this one. So this one is different, right? So now if we consider self like this one, scalar product of itself, let's look if this exists, that we also finite. So example dimension must be finite. That is from here. This is any scalar product between two different vectors or function vector functions. But then, if this satisfies, this must be satisfied because this is itself, right? It's one of the scalar scalar products. And this integral we call the square integral since this is itself is a square, right? So this one. Now, in one of these property in the function space, how about dimension of the function space? How much the max number of the basis vector? That is infinite. So that is different. In this in this function space is infinite. Okay, that is because this series, for example, is expanded in terms of infinite number of linear numbers, infinite number of linearly independent functions. Okay, example. Consider any function have a Fourier transform, right? So any function we can extend in terms of a Fourier transform, which is sine, cosine. Those sine, cosine form the basis because they are linear independent, and you harmonize that's infinite. For example, any like we can have one of the Fourier transform expansion. Fx we can expand in terms of this sinusoidal function. So n from 1 to infinite, how many we have? Even an cosine nx, right? N must be infinite. If not infinite, it will not cover the whole space because the basis is maximum. The maximum should go to infinite and plus the sine, right? So how many we have? Infinite basis side, which form this maximum number of vector form this space. So dimensions is infinite. En sine nx. Okay, so those are these Hilbert space vector and the behavior which we introduced. Now you can see here those vectors. We here I either use the function or I use the notation, but we know in general we are going to get rid of any detail the coordinates correspondent to express vector. We are going to use like abstract notation, so that we introduce the so-called Dirac notation. Those are the notation we always use in quantum mechanics. The reason is because for a vector, if we consider this different type of coordinates, for example, in Cartesian we represent vector R, we use this x, y, z components, right? So that is x, y, z. We represent this. But if in the matrix, in the matrix, this is a column matrix, right? So the R actually is A1, AN. This is a column matrix. And we are going to use this later. Also, another way, in the matrix representation, we are going to represent the vector, which is a column, and its complex conjugate is row, right? So now, if in the function space, it is a function which we are going to also use. If we go to the position representation, or we try to correct this wave function, we are going to use this. So those are the details depending on which representation or which coordinate we are going to use. Then we are going to introduce, if we try to introduce a free the state vector, which we are going to use in quantum mechanics vector, in quantum mechanics from in the coordinate, detailed coordinate, we introduce Dirac notation. That is the purpose. Okay, if we say that way now, what is the vector? So now first we are going to introduce cat, which is use this.
I didn't get
Yes.
this. Free the state.
Free the
I didn't get this. Why
from.
we introduced Dirac notation?
Which one?
Means you said that why we introduced Dirac notation.
Yeah, why? Because we want to get free. That means do not depend on any detailed expression, coordinates or matrix. We just say this is state. So yeah, that's like abstract, right? We just consider use this notation, and this notation, if you go to the position representation, it will be this one. If you go to matrix, it will be this one. But we just use general to represent this. And when you go to the detail, you have detailed expression. So we just try to free from these coordinates. We introduce this cat to describe, to represent the vector. Yes.
So this is Dirac notation is directly just describing the physics of the issue, not necessarily the math, which is with the matrix and the Cartesian
Yes.
coordinates.
Okay. So this like abstract, we just consider we use some symbols to say that is represent the vector. But when we go to the details to deal with the system, you need which representation, right? You need to solve like Schrödinger equation. We have to go to the Cartesian or go to the position representation, or maybe you go to the momentary representation. That is the end of chapter 2 we are going to discuss, and matrix representation. But they all represent, for example, vector. So the state vector in quantum mechanics, we may use this way, or this, but they all vectors. We are going to use this notation, and then when you go to details, you're going to project.
Depend on.
Yeah, depend on which one you're going to. So we are going to how to from here to here. Later we are going to discuss. Okay. All right. So that is cat. This means a vector. We are using notation to vector. So use a cat to represent vector. For example, here. Remember the function space. I use the function, right? Now I use function put into the cat. So that is the correspond to this particular vector. You can also use psi 1 or phi 1, whatever, right? So those say, okay, they are cat. The cat, different cat, right? So I mean, correspond to different vectors or state vectors. We use those. So that is they give the vector. Then correspond to this, we have a bra. It's just reverse. So bra, you can see this is go to this way. So that is the element of vector, and the bra is element of a dual space. example, you can have a bra psi or bra phi 1 or psi 1, whatever, right? So, what is the relation between cat and bra? Okay, that the relation, right? So now relation between cat and bra. They are always correspond one by one. So once we have a cat, there must be in the dual space, there must be exist a bra. So that is always one by one correspond. That is for every cat. Okay, there are either this unique bra and vice versa. So if there's a bra, there must be a unique cat. Okay, now once we have this, you will see this. What does it mean if we have a product of this bra multiplied cat? That is inner product. So you will see that you can image that bra like a complex conjugate of the, if a psi is vector, its complex conjugate psi star is bra. So here the inner product is the inner product or product scalar product. It is a scalar product. Okay. Of cat and bra. Okay. Example, if we have the inner product of this cat is phi, right? Phi cat multiply the bra psi, that is equivalent to, we have, and the equivalent to in this space function, that is integral. For example, I use one dimension. So once you see this, that means this. That means scalar products. And you can see here, that's why they correspond one by one. Okay, now we have, when we introduce those, we are going to discuss the property of this direct notation of those, because sometimes there's some confused, so I want to just give you examples, and hopefully, I also give some homework to do exercises on Thursday. I want you just try to familiar with those. Maybe you're already familiar. So now, if we have now, if I write this way, what does it mean? It is cat, right? And the cat inside is scalar, multiply this one, so that's equal to, and take scalar outside. That is equivalent. Okay. Now, how about this one? This is bra, right? Equal to what? Is that correct? Good. So it's this, right? Okay. So because bra, so then when you take out this scalar, you have to take the complex conjugate. If a cat, you just keep the same. All right. So now, I think, okay, just a moment. And here, this is a scalar product, right? Between this one, I think I did I erase? The scalar product is equal to its complex conjugate, right? So in the direct notation, that is equal to, the change is flip right, and then that is same thing as before. So use direct notation like this. And be careful, it is not equal to, right? Only when they are real. If not, they have a complex conjugate, so be careful here. And now, in general, I think this is simple. I just write down here. That is a cat, addition of two vectors, and the inner product is a bra. So that is, take this constant outside, a scalar outside, because this is in the cat, right? So I can take here. Must be But oppositely, if we have A psi 1 plus B psi 2 psi, that will be A star and psi 1 psi plus B star psi 2 psi. Okay, I just write down here, I think you can do yourself. A1 psi 1 plus A2 psi 2 bra, and multiply the cat is B1 phi 1 plus B2 phi 2 equal to. Write yourself. Any question? I think here is easy, right? Okay. Now, more. This one actually is correspond to, we define this, the norm, right? So if this cat and bra multiply itself, so that is equal to, because this is this one, since they're same, so they are equal, and that's real and positive, right? This is usually, if we write down this means this, and that is real and positive. Okay, there are another two very important inequality which we are going to use when in particular we discuss this.
Professor, you missed this one.
Yes. In particular, we will introduce, no, this one, okay, if I have double, I mean this. I mean, let's just follow text notation. Usually, maybe you write this way.
Yeah.
Is so. I hope that is equivalent. You just yeah. But of course, you keep in your mind yourself, right? With which way it means. All right. So now we have two inequality which important we will prove. For example, uncertainty principle, Heisenberg uncertainty principle. We are going to derive mathematically. At the beginning of the chapter 1, we just introduced Heisenberg assumption with the product of delta x and delta px be always larger or equal to the half h bar, that gives an uncertainty. Then we are going to prove in chapter 2. So we are going to use those the two inequality. One is a Schwarz inequality. This means if we have this norm or magnitude of this inner product square, so you see here I use square because if otherwise you use double. Yeah. This square is always equal or smaller than this product of each norm. This one is, I will not prove because we do not want to spend time on this math. But simply, you can see here, it's equivalent to, if you consider we have two vectors, that is A, this is a B, right? So we know the A inner product B, like this, that is equal to A, B, cosine theta, right? If the theta is 1, if they're parallel, then that's same. This will be set equal. Otherwise, it's always smaller than this value, right? So that is you can see, you can easily compare with this. So they are very easy to understand, so I do not prove that. Second one, another inequality, we call this triangle. Inequality. This one is square root of the additional two vector and the inner product of addition of two vector. Should be always smaller than or equal than the addition of each individual product of this one is also easily to interpret in terms of the vector addition. So very easily, I'm going to just give you. For example, we have A, we have a B, and the addition of A and B is here, right? That is A plus B. So in this case, you can see here, here. So A plus B, the magnitude of A plus B is this one. Definitely it will smaller or equal to the A plus B, right? You see A plus B is longer than this, right? So that is the equivalent. Then you can see here this one is correspond to this, and this one is this like this. So this way can help you to remember these two inequalities. Okay, now one more is what is the if the states are orthogonal? When we found this Dirac notation to characterize if the states are orthogonal or the two vectors are orthogonal, states is if this inner product is equal to 0, right? Okay, that is very simple because we know like perpendicular. And also normal, if we say that is also normal, also normal states means this if these two states first 0 and each norm are 1 and books. So that is normalized. And in quantum mechanics, we are going to do this. Each time when we solve the Schrodinger equation we give the states, we first want to normalize. That's because we know the probability is 1, it's not larger than 1. So if these two states are orthogonal, we need this. Now, one thing is forbidden, so be careful when we use the Dirac notation. This pattern is forbidden, it's not correct. So what is? You cannot have these two bra multiply each other. So there's no bra or cap. This does not exist. So when we have, because you know, we know there's a two vector, the product, either inner product or cross product. This never represents the inner product nor scalar product. So that is not, because if you have this mistake, something wrong, right? So you need to be careful. Okay, very good. So now we deal with this vector that since we will, in the chapter 3, introduce postulation. First postulation is about this feature of the quantum states, which is be characterized by wave function. And the behavioral wave function follow this. So in that time, I will not mention the details. You just assume you remember those. Okay, now that's state. Next question, in quantum mechanics, how to describe or characterize the physical quantity? I can erase this now. Okay. A, B, C, D, right? Operators. That is quantum mechanics correspond to the physical quantities. That means quantum mechanics we need not only states but physical quantities. So mathematically, in quantum mechanics, how to characterize those physical quantities, we introduce operator. Now the operator, the definition of it. Okay. Suppose we have the mathematics, right? We are going to use mathematics to represent operator. If it applied, it is applied to a vector. So if we have operator A, let's just use, now we use notation here. A hat. To distinguish quantity, physical quantity A without hat is a physical quantity. It's a measurement the real value, or in particular most cases the positive value or real value. But here we use A hat. So if the A hat, if it is applied to that and a cat, right? So we have a cat, and it will then it transform the cat to a new one, transforms the cat to a new cat, not new operator, not something new scalar. It still keep the cat. That is the function, or we define this operator. So what this means, mathematically, apply the cat, right? So that gives us another cat that's new, separate. If this is the case, then we say that is the operator. If it give you a scalar, that is not, right? If it give you some others or another operator, it is also not an operator. So that is we define. If we have this operator or this applied to or a cat, we give a new cat, okay, we call that is operator. That is also the mathematical expression to give this relation between the operator and the cat. Now, that is the cat. So, or we have either cat or bra. So in this case, for bra, we have use this. So the operators not at left-hand side, be at the right-hand side of bra, and that gave us a new bra. Right, so these two exist. That is the operator. All right. Okay. Now, this is something new, so now let me give you some examples, and we go to details to discuss the property of operator, type of operator. So what kind of things we can have this example? Let's consider one case. For example, we have if we have operator, if we have this applied cat, still give a cat, we call this I is a unitary operator. Yeah, yes, it is still transferred to another cat, but it's itself, right? So we call this a unitary operator. That is one operator. Another case, if we have, I'm going to use the grading. You know, that's a grading of a function, right? And this function, we know that gives us partial x, y, partial y, j, right? partial z, k. So this is operator. And we call this operator is grading operator, right? This we will use in quantum mechanics. And similarly, we know there's another, we call the Laplace operator is also an example. So usually we use square. That is partial square, partial x square plus 1 square, partial y square, partial square, partial z square. Here, I also want to mention, you see this is vector. So this operator maybe is a vector operator, that means has its components, or just scalar operator like this. Right, so that's the whole output. So we call this is Laplacian, right? So this one, Laplacian. One more example is if we have an operator applied to this state. We give a new state, but that is, it is just reverse R from R to the minus R. So this operator, we call it P, is a unit or a parity operator. We have more other operators later we are going to discuss. So this just a brief examples show what does mean. Operator by definition you see, yes. This one, after this give that this another function that is secondary duty. Right? This one give another these vectors. So those are operators. Now, first we discuss, can we multiply operator and what is a product operator? Yes, that is it. So now operators, and then let's use definition. Maybe I'm going to use 1, 2, deeper down of operator. How the operator multiply each other? So here, if I have A, B, be careful. Yes, they can. Okay. A, B can get another new operator. So the product operator gave a new operator. That is, and be careful. A, B is not equal to B, A. So that means we cannot change the position. Yeah. You know this not commutative. This is not like. The scalars. That is very important. First, we know the product operator, how many product operators you give an operator. Second, the product operator, you cannot change the position. Okay. Third, so, but if we have a product, yes, we cannot change the position, but we can operate, multiply, for example, first B and C, and then multiply A, or first A and C and multiply A and B. That is okay. So here, the product of A, B, C, 3 operators, you can either look the first write C and B and then multiply A, or you first look this left hand side A and B and then multiply C. But you cannot change the position. You keep the position, you just group which one you want to perform first, right? Second. So that is this is a search for this. Here in the properties. Then okay. So when the operator, product operator, apply the cat, how to do that? You can first you have to keep the left hand side first. You cannot A apply cat first. Which one close to the cat first? You can. So that's equal to B cat. Apply the cat first, and then go to A. If this is a prime, psi prime, here psi prime is due to the operator B apply to the cat, right? So that just follow this. And again, if A, B, C, you should also follow the order. You cannot change order. So here we have A, B, and C first. Then we go to A and B psi prime. And then we go to A psi double prime. So here, psi prime is a C applied cat is psi prime, and psi double prime B applied psi prime, if a new one is psi double prime, and then A applied. So step by step, be careful the order or the position we cannot change. That is not like the scalar numbers, so be careful here for operator. It's very strict, very strict. So now we are going to discuss the sandwich. A is sandwich. between cat and bra and cat. What give us? Okay. That is a cat and bra. So when we have the operator is sandwiched by this, what you will have? A vector, operator, and scalar. Who give me the answer? Vector, operator, and scalar. Which result give us? Scalar, right? Because here, when the A applied cat give a new cat, then this inner product of the cat with bra. So that will be scalar, right? So that is scalar. That is different. And then we'll count these numbers. Scalar is usually complex numbers. Okay. And here, this one, there are two ways. So be careful. This also equivalent. Now, I can first, as I mentioned here, you first use the A operator applied cat. So you gave this, do this way. Or I'm going to use A applied the bra. Then, so that is, and they are equivalent. Okay. So when you have sandwich, you can use apply the A operator either apply to the cat or apply to the bra. This we equal, right? That is the property. All right. So now the product is not 3. Okay. We are going to discuss some linear operator, since those operators are in this quantum mechanics. Most cases they follow this behavior. So what is a linear operator? If the operator follows this, so if A apply the linear addition of 2 cat with this product of the scalar product and like multiplication, scalar with cat, and then addition another, so this is another cat. Then A apply this give another cat, but we can also separate it with A first apply this, get a new cat, and then A apply second term. Then the addition of 2 vector, right? So that is, you can do this with A. Since we know the scalar doesn't, the A only apply to the vector, not act on this, right? So I can take off in front of, move to in front. Okay, and in other words, they are commute each other. So A hat multiply A1 equal to A1 multiply A hat. Later we're going to say that is commute. But here, at least to give you the idea, the operator only apply or change the cat or bra, not the numbers, not scalar. So I can put here. Then, so what you mean is, if you deal with this, you just direct go to the A apply the cat. You just move this as the constant outside. That is this one. And second one, bra, same thing, right? So if we have a bra, A1, okay, now I'm going to give you some additional, just be careful. Here, I'm going to ask you. So now A, I think I remember I mentioned, right? So when A apply the bra, A is at the right hand side, cannot go to here, right? Forbidden. Okay. Now I'm going to ask you, this is equal to that. If the A1, do you agree? Do you agree? Yes or no? Yes? That is no.
Oh, this.
Because this is outside,
Yeah.
right? So be careful, yeah. If inside, that is I'm going to say, if this one, then you have this complex conjugate go outside, right? So that's be careful. Depend on where the scalar position. So now this A1, so state 2, star, side 2. Okay. Yeah. Later, that some of the exercises I will let you to play and try to familiar with those. Do not make mistake when we deal with the representation. Actually, the property of the operator, cat, bra, and scalar. That is a linear operator, and then I think that's D. Okay. In the linear operator, when we have introduced expectation value, when we say expectation value of operator, or sometimes mean value of operator A. How to determine this? By definition. So we are going to use notation. This means the mean value or expectation value. We have this cat, not sandwich between the states, right? So that is one of the example we have some sandwich. This one, right? But now these are two different states. Expectation value is the same state, right? Okay. So that is a sandwich between the state cat bra, the same states but normalized. So denominator we have this scalar or norm of this vector side itself. That is expectation value. Okay. That is also introduced. What is expectation value? Another important operator. We call this this one. Operator is okay. Cat and bra are vectors, but if I use cat, not bra in the right hand side, the cat in the left hand side. So that is an operator. It is a linear operator, and you will see this one is very important. Later we will see we always use this. And one way is we want to try to transform from one basis set to another basis set, or project the cat to one of transfer. If they say they multiply this cat, so what that means is transfer the cat or project cat to this. Let's just later you will see how important it is. So this is operator. Okay, be careful. This operator, it is not it's different from inner product. Inner product just move this one to the left side, right hand side, right? Just opposite. The cat multiply bra. If inner product is bra multiply cat. So for this one, you can see here what is example, right? So example how to apply this. We have this operator apply to another cat, and you will see this one is a scalar product. So you will get that something is like this scalar. So I can move this one to the form, right? Because it's numbers. So what that means? Initially, this is a vector space, precise space. But now when we apply this, we go to another space, formed by side. This is formed by side, right? And later you will see this, how important it is. And as I said, some are forbidden, right? So I mentioned again, but let me just try to emphasize forbidden product. Okay, this product means, for example, the cat, but operator at the right hand side. This is not, right? So we cannot. The only operator apply cat. So operator will be at the left hand side and the cat on the right side. But this one is not. Or you have this operator at the right hand side with a bra. This is not correct. The correct one is bra first and operator A is the right hand side. So that is the correct one. This is a forbidden. Okay. Then we are going to discuss some of the particular operator, why is not important operator, permission operator. We are going to let you know the quantum mechanics all the physical quantity corresponding operator are Hermitians operator, right? So now we put that. Hermitian. Okay, Hermitian. When we discuss this, we are going to use the what is Hermitian and John. Or conjugate. So what is Hermitian and conjugate? This is not only for operator, for the scalar and for the vector CAD and graph. We're going to give you this correspond to each one. What is Hermitian adjoint and conjugate? First, for number or complex numbers. So when we are going to use, use dagger as notation. So when we say what is a Hermitian or conjugate of this scalar or the CAD or vector or operator, that means if we say that if this A is scalar, that is equivalent to its complex conjugate. So when we do this, you just know that it's just take this complex conjugate. For the vector, if for vector, what is for vectors, its conjugate or Hermitian adjoint is just CAD and graph. So now this is a CAD, right? The conjugate or Hermitian adjoint of this CAD, I use this notation. This is a CAD. I take this, that equal to x graph, right? Okay. Or let's say this graph. If you say graph conjugate is CAD. So that is the for the CAD graph. When we have this notation, you know what how to do. Then for operators, okay, the definition of how to define A dagger. That is if A dagger is defined such that the following equation satisfied. So if we have the sandwich of operator A dagger between the graph psi and the cat phi, that equal to, we take this so this is a sandwich operator A, right? But if the sandwich operator between the cat psi and the graph phi take the complete conjugate, then correspond to that inner sandwich, that operator will be A dagger. Little bit confused, but just if this is satisfied, so we have two operators. This is just assume another operator. So the operator, new operator between this one, if equal to the old operator which changes position and takes the complex. If you miss this one, it's not equal. You must have this one. After this and take this, then you find the new operator. So the relation between A dagger and A is satisfied. Okay. So okay. Let's some of the we are going to make those together. If we have this product with the numbers with the CAD and operate together, then we take the complete conjugate. How to do that? Right? So that is some examples how to perform those. For example, A dagger is dagger. S will be equal to itself. So when dagger takes dagger, that's a back, right? So that is first one. Then if I have for A, the scalar multiply the A and this dagger. So when we do this first, okay, that A take this one, right? So that is A, then A dagger. The operator, it is dagger, and the scalar takes the complex conjugate. let me do more. So we have, if we have a to the ever to the nth power is dagger, and you will play by formed by this or by the right. So that is, you can easily see that is a dagger to the nth power. But if AB, be careful. This is itself, right? So they multiply n times. It later you know, but when I say commute each other, right? So that is equal. And now if we have A plus B plus C plus D, this dagger. Because this addition, it will not affect, so equal to each individual dagger. Okay. However, the product of the operators, the dagger of product of operator, this, be careful, that's equal to the each individual operator, the dagger of each individual product, but change the order. So here, D is last, right? Then now D go to the first, or go to the left, the most left. D dagger, and then C dagger, you just try to counterclockwise, right? C dagger and B dagger and D dagger. See here, just to replace the position with take the counterclockwise or clockwise, whatever. So that is be careful here. Then if we have A, B, C, D, apply the cat, then we take this dagger. Cat, go to bra, right? So bra, then the position. So now this is a D dagger, C dagger, B dagger, and A dagger. Also, the position change. So all the operators will go to right. Since only the right, I think I have about forbidden, right? Yes. This is not this. This is also not this, right? For the bra, you have to go to here, go to the right, and then change the order. Okay. Now, since I introduced this one, right? Let's look what is the Hermitian agent of this operator. So this one, this bra became cat, and then position, right? So you have to change the position. Okay, so that is cat became bra, and bra became cat. Bra became cat, and the position should change. That is how you deal with this. Okay. Now, then one more, I think, also just one more, and then I will go stop. So if we have A, okay, this all together, so there's A, and the scalar A operator. Okay, so this one I think is already. All right, so now this one. This one. A, because this is a bra, right? So let's take outside to this one. And this one, okay. So now I keep this one, the bra, but A should go to here and do that. That makes sense? So if the A operator is inside the bra, when you take outside, we go to the right hand side and take this conjugate. Be careful. This is if outside is different, right? If this outside, you keep outside, but you cannot keep here, right? Because this is forbidden. Only one is here. But if inside the bra, when you want to take outside the bra, you just be careful. The operator speed take its Hermitian adjunct and also go to the position, right position. Let's see, last one. Okay. let me see. I think this one is, let me. So this one, again, we know this, we go outside and they go to here, then A dagger become A, right? Okay, last one. And you finish. I know. You don't have a class, right?
Yeah.
No,
Okay.
I don't.
So, yeah, a sandwich. If I want to take inside, so we go to the A dagger, right? So that means A dagger, we are weak. Or, so when you want to operate, when you have an operator sandwich, if you go to the cat, you keep the same. If you go to bra, you have to take complex conjugate. All right, so now let me stop here. I know this the details when we play. If you here, if you know those the basic, then you can deal with each. Okay. So I'm going to assign homework on Thursday to give you the chance to play this. It's okay?
Yeah.
How about this, Navi, that's okay? I
Yeah.
can use, okay, that's the sheet. So whatever. All right, see you tomorrow.
What's the homework?
What's the homework?
No,
Next
on
week?
Thursday,
On Thursday?
Oh, okay.
not today.
Okay,
Yeah.
okay, that works.
I said Tuesday.
Yeah, we were waiting for.
Yeah,
Oh, sorry.
I thought we were
That's
gonna.
why I thought you were waiting for what? I said Thursday.
I
No,
thought you-
today you only start to have something, and Thursday I'm going to discuss more.
Okay, okay.
Then you will have, yeah, Thursday. Sorry.
Thursday or Wednesday?
You have a question?
No, Wednesday.
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 No. Thursday, I mean, Wednesday, yes,
Yes.
you are right. Yeah, Wednesday,
All right.
yeah.
Let's
Today is Monday, yes. Wednesday for quantum mechanics homework.
Wednesday homework, and it's due Monday or Wednesday of next
I
week.
will give you 1 week.
Okay,
Next, at
Wednesday.
least next Wednesday.
Okay,
Next
perfect.
one, next
Okay,
one.
thank
You
you.
have 1 week at least.
Ads. I don't remember how
Yeah,
it
next
stops
class
recording this, but
No class.
Tomorrow you have?
Yeah, 2 classes.
Today you have class?
No.
that's my only class. I don't know how to turn that thing off though.
Just press this. You have to just press this.
Oh, the button.